Welcome to the 8th live session of Fundamentals of Additive Manufacturing. So today we'll be discussing on MIG and TIG wire additive arc additive manufacturing methods. So let's start with the questions. So which processes separate control over the wire feeding process? MIG, TIG or plasma wire arc additive manufacturing process. So before we go to the answer, we'll discuss what are the wire feeding processes in all these three processes. So in in thick warm process we have separate control over wire feeding process. So we now will discuss it in detail. What happens in TIG warm process? TIG is tungsten inert gas welding or gas tungsten arc welding process. Here an inert gas shielded arc welding process is used where it uses the non-consumable electrode. Now here as we know, suppose this is the setup of a TIG welding. So here in the down below region there is a wire and a tungsten electrode comes. Now there is a welding torch at the center. This is the tungsten electrode. The non-consumable electrode creates an arc which creates a molten pool. This creates a molten pool in the in the substrator rebuild layer. Now an inert gas is supplied to the welding zone through the annular path surrounding the tungsten electrode to effectively displace the atmosphere around the molten pool. So now here in this process a filter wire is fed towards the molten pool, which after getting melted deposits the material on the substrate. So unlike MIG process, here there is separate control over the wire feeding process. While in MIG, there is no separate control over the wire feeding process. And the plasma cladding process, this is quite similar to the TIG cladding process. Here also we use a non-consumable tungsten electrode to produce an arc at a workpiece. Now, plasma is here in this case the tungsten is not projected outside, hence this is somewhat different from the TIG warm process, but here in the TIG process the tungsten is projected outside. So in this way the TIG and plasma are a little bit different. And moving to the MIG process, what happens in MIG process is here the wire feeding process, like here the consumable electrode is in the form of wire reel. Now the electrode and the workpiece are connected to the welding power supply. Now here there is a consumable electrode. In TIG process there is a non-consumable electrode. So this is the major difference between MIG and TIG process. This also we know from our manufacturing processes. And thus the correct option is option B. Okay, let's move on to the next question. How is plasma cladding and TIG cladding similar? So, both plasma cladding and TIG cladding methods, they use a non-consumable tungsten electrode. So, option A is correct. And inert gas is only used for shielding. Bead height can be increased significantly. Now, this happens in plasma cladding and TIG cladding. Both use non-consumable tungsten electrode. This also uses non-consumable tungsten electrode. Now this electrode, it is used, as we already discussed previously, this is used to produce arc at the workpiece. While in plasma welding, we have the shielding gas. While there is no such shielding gas in TIG process. And already said that in TIG cladding process, there is a separate control over the fire feeding process. Now, in TIG welding, we have an inert gas which is used only for shielding. So this is for the TIG cladding. This doesn't happen in plasma welding. While in plasma welding, what happens? The shielding gas is divided into two parts, which we know inner core and outer core. Now inner core and outer core. Inner core and outer core. So inner core is used for ionization and establishing the arc, and the outer core is for the shielding process. Now this is the major difference in plasma and cladding. Apart from the previous difference which you already discussed now, that here the tungsten is projected outside in TIG cladding, while in plasma cladding the tungsten is not projected outside. And since the tungsten is not projected outside in plasma cladding, the bead height there can be increased significantly. This is only in plasma cladding. This is both. This here in outer core and inner core. This outer core is for shielding purpose. Outer core is for shielding purpose. And the inner core, it is for ionization and establishing the arc. So, okay. So, moving on to the next question. Which of these are correct for reverse polarity in DC arc welding? So, correct option is less heat is required at the workpiece side and polarity can be reversed by making the workpiece as negative. The options are B and C. So now we will discuss what is this reverse polarity in DC arc welding. Now, in WAM systems, wire additive arc manufacturing, there are two types. One is AC machines and DC machines. Now, we have DCEN and DCEP. Now, this is known as straight polarity and this is the reverse polarity. Now, DCEN is direct current electrode negative, DCEP is direct current electrode positive. So, now DC arc welding is generally preferred because of the control of heat offered, input offered by it. Now, in DC polarity, what happens when more heat is required at the workpiece side, the workpiece can be made as anode, liberating large heat near it. This is known as straight polarity. Now, what happens here is more heat is required at the workpiece side. Now, workpiece can be made as anode workpiece can be made as anode and large heat is dissipated near it. Released near it. Now in DCEP, direct current electrode positive, which has the reverse polarity, what happens is less heat is required to produce on the substrate. For this, the polarity can be reversed by making the workpiece negative. Less heat is required at the workpiece side. So, workpiece can be made as negative or cathode can be made as negative and less heat is required on the substrate. So according to these difference, the correct option for reverse polarity in DC arc welding is less heat is required and polarity can be reversed by making the workpieces negative. Okay, so moving on to the next question. What happens when the residual stresses is more than the ultimate tensile strength of the material in wire-based additive manufacturing? Okay, so here there are various scenarios. As we know, the defects. No, the answer is the cracks. So we'll discuss on that. Correct answer is A. Now, first we'll discuss residual stress. What is residual stress? Remaining stress in the part after removal of all the external forces. Now, if the residual stress is more, okay, sorry, there was some lags. So residual stress greater than UTS of a material, crack occurs. Residual stress less than UTS and more than here warping or plastic deformation occurs. Now in this case, when the residual stress is less than ultimate tensile strength of the material, this can be, obviously this is more than the yield strength of the material. When it is more than the yield stress of the material, more than the yield strength of the material, then at that point only warping or plastic deformation occurs. Now it is, as we know, it is impossible to eliminate, like we cannot avoid residual stresses from the parts produced. But if we follow some proper tool path strategy, then the magnitude of the residual stresses can be subsequently reduced. Now, and the residual stresses in the part, this leads to loss in geometrical accuracy. It will also affect the fatigue of a part. Like there will be various distortions in the part. This will lead to loss in geometric accuracy, and this will significantly affect the fatigue life of the part. Okay, so so this is one of the defects of wire arc additive manufacturing: residual stress and distortion. Apart from this, we have porosity, crack, and delamination. These are the major defects: porosity, cracks, delamination, and residual stresses, then distortion. Moving on to the next question. Which deposition method is the most suitable for pulsed wire arc additive manufacturing? Yes, pulse metal transfer is the correct option. So we'll discuss why. There was my voice was not coming. So we know there are various deposition processes. There are various deposition processes. So first we'll discuss briefly on the metal transfer is done in various ways, in different ways, and these are some of the methods. These are the methods. Apart from this, we have another method which is rotating spray transfer. So, what these methods are found to occur with different rate of current. Uh, the metal deposition rates, um, these have different rates, like according, but we the most suitable we find the pulse metal transfer for this wire arc additive manufacturing method. So, thing is, in all the, like in spray metal transfer, in rotating spray metal transfer, globular metal transfer, short circuit metal transfer, we have various varying wire speed, voltage, travel speed, shield, different sizes, different mm, size of the electrodes. These all processes vary, but and also the deposit rates, these are also in different ranges for these different methods. Now, this is dependent on the current direction, on the position of the forces with which the liquid drop is deposited on the arc. So these are the things which are varying in these deposition methods. So basing on all those parameters, the pulse metal transfer is the most suitable method for uh, wire additive manufacturing. Now, in the pulse spray method, the deposit rate is 0.92 to 0.7 kg per hour. Okay. So, moving on to the next question. In MIG welding or cladding process, how is the wire feed in synergy with the welding current? So, here we know in MIG welding process, the wire feed is linearly proportional with the welding current. Now, this is suppose the current, and this is the wire speed. This is in meter per minute. Now, this is linearly proportional. Now, it follows a linear curve. So, the correct option is answer B. Moving on to the next question. In an omnidirectional additive manufacturing process, how is the geometric or metallurgical properties of the fused layers are related to the direction of movement of fusion source in the XY plane? So here you would be having an idea on the, like what is the omnidirectional method in a additive manufacturing process. The correct answer here is the omnidirectional process, it is independent. Now, omnidirectional, this means equal sensitivity of the process in all the directions. For that is, the geometrical or metallurgical properties of the fused layers are independent to the direction of movement of the fusion source in the wire. So there are different, as we know, for this omnidirectional, there are different different methods, like There are different methods, like first is coaxial, feedstock and fusion source. Then it is coaxial, fusion source and surrounded by feedstock. Next is coaxial, feedstock and surrounded by fusion source. And the last case is when we dynamically adjust feedstock feeding direction. So the first option is where the coaxial and feedstock and fusion source, what happens is this is the feedstock, and this is the fusion source. Now VW, we name this as VT and this is VF. VW. Similarly, for the second case, we have the fusion source is upward and Vt, and this is the velocity of the feedstock. Now for the third case, this is the feedstock and the Vt is directed towards this direction. And for the last case, this is the fusion source and the feedstock is directed at an angle VW. So these are the major four cases of the omnidirectional principles of different methods of obtaining omnidirectionality. These are the principles of different methods of obtaining omnidirectionality. Moving on to the next question. What type of defects are likely to occur in MIG wire arc additive manufacturing process when a layer is deposited on a substrate which is not cleaned properly? The correct answer is porosity. Now, as we already discussed, there are various defects occurring in wire arc additive manufacturing process: residual stress, porosity, crack, warpage. Now, here we already discussed some of these methods where how the residual stress occurs and what happens when the residual stress is greater than less than the ultimate tensile strength of a material. So when according to this, the residual stresses occur when the residual stress is greater than the UTS of a material, the crack will occur. Now here, when a layer is deposited on a substrate which is not cleaned properly, porosities occur. Now, when this porosity is present, it leads to low mechanical properties and fatigue life. Now, these porosities have two different categories: raw material induced and process induced. Raw material induced porosity and process induced porosity. This occurs due to surface contamination, and this occurs due to poor path planning or unstable process. And the porosities, these can be controlled by various methods such as cleaning of the wire and substrate, process monitoring, high quality shielding gas, and we can optimize the bead shape. These are some of the methods where we can decrease the porosity. And the apart from the porosities and residual stress, we also have crack and delamination. And the crack and delamination mostly occur due to high temperature and material characteristics of a additive manufacturing method. There and the cracks are also of two types: solidification crack and grain boundary crack. Now, delamination this occurs when there is incomplete melting of the substrate. The defect is that is clearly visible, and that mostly it is difficult to be repaired by the post process treatment. So to prevent delamination, we need to do various uh, pre-process treatments such as preheating. So these were the questions which were to be discussed in this topic. So if you have any further doubts or any other queries regarding the assignments, you can ask.
Madam, if you can just just assignment
Mm-hmm.
that
Okay. Yeah. Yeah, please. Yes, yes. It is linear. Yeah, yeah. Actually, see, you can refer that in the there is one image, sorry, picture, some figure where that feeding mechanism has been shown for that TIG worm. So I'll just say you also where to refer. Um, yeah, it's not clearly mentioned. That's correct, but that is in that figure. I'll just say you which slide page number. So there you will be seeing it will be front like different types of feedings have been shown. Just wait, let me get to the slide. I'll show it. Hmm. Yeah, that is correct. So it will be difficult for you to imagine. Hmm. Ah. Yeah, yeah. But still, I think in this they have done it very picturesque this time. Hmm. Yeah, yeah. That will be difficult unless until you do operate the machine on your own. Uh, yeah, 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 yeah. So where are you working? Okay, 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 okay. Mm-hmm. Uh, act, 11th number. Mm. 11th number question. Did you like just try solving it? Because I think it's a direct formula question. I'll just say you the formula also. Uh, I'll just write this formula.